Hi everyone. Let's start a new unit. Unit 9 is buffers and titrations. Let's start with what are buffers and how to make them and how they work. These memes are actually for titrations, and if you've done a titration in the past, you probably know exactly what these mean. But for this video, we are starting with buffers, and section A. What are they? Buffers are solutions that resist change in pH when small amounts of acid or base are added. A buffer solution is literally buffering. It is buffering the solution from wild fluctuations. I don't think that's how you spell it. If you think about where people use buffers, probably mostly they use buffers in biology, because with cell studies, or if you're doing in vitro drug interactions. You want to mimic what's inside of a cell, and physiological pH is 7.4 typically. It's around 7.4. Okay. Give me one sec. I'm working with a new setup here. Let's try. Okay, let's try that. All right, part B. How to make. You're going to mix a solution of a weak acid with its conjugate base. Let's take this weak acid. Maybe we have 500 milliliters of each, and we're going to mix them of 0.10 molar HCN. And then what is its conjugate base? Its conjugate base is Cn minus. But when you go into the stock room, you're not going to find Cn minus. You're going to find it as a salt. And maybe you'll find it as, let's see, we'll use the same concentration, but when you make up this solution, maybe you'll find it as a potassium salt, KCN. But you know that in water that is going to ionize because it's very soluble. It's the metal. The metal is a group 1 metal of the salt, and you get the Cn minus. Okay. Weak acid, conjugate base, check and check. Or the other way to make a good buffer is a weak base, and its conjugate acid. A base that you should be very familiar with is NH3. Maybe we could take a 0.3 molar solution of NH3 and mix it with its conjugate acid. Let's take 0.20 molar. Concentrations don't matter right now. And now what is the conjugate acid of NH3? It's actually NH4+. But again, when you go into the stock room, you're not going to find NH4+. It'll typically be sold as a salt. And we could find likely NH4Cl, ammonium chloride. Okay. Remember why this is a base? Just as a reminder, because we don't see any hydroxide. So some of you may be confused. Why? How's that a base? We don't have any hydroxide. It is picking up a proton. That is the Bronsted-Lowry definition of a base. And in water, it can do this. NH3 plus H2O goes to NH4. So I'll separate these. Normally they end up together as an ionic bond plus OH minus. Okay, there's your hydroxide, and that's your base that picked up the proton. So this is a good way to make a buffer, weak base and its conjugate acid. Now, there is one way that kind of confuses students, but it's a classic exam problem. Is this a good buffer? If I use equal volumes of, or maybe I should say in 1 liter, I have 0.50 moles of acetic acid, CH3CO2H. All right, that's acetic acid. Oh, let me scooch this up a little bit. Get acetic acid plus conjugate base. Oh, no. I want to see if we can figure out what happens if we use a strong base. 0.20 mole of NaOH. Okay. I'm warning my students, with the multiple choice problems, don't go with your first instinct if you're not working out the problem, because it could be a trick, or you may need to do some deeper thinking about it. Because on the surface, this looks like a weak acid and a strong base, and it's true, weak acid, strong base. So initially, a lot of students will say this is not a good buffer. Weak acid. It's not even the conjugate base. It's a strong hydroxide base. Okay. But what do you have to realize, especially now that amounts are important? If I put these together, the reaction that you would get is CH3CO2H plus NaOH goes to, see, the hydroxide picks up a hydrogen, H2O, but more importantly, you're left with the conjugate base. CO2, and it's minus, and you do have the sodium plus. Okay. Sometimes the professor will write these together as a complex. But oops, there it is. There's your conjugate base. Now we just got to make sure that in this solution we still have a little bit of the weak acid and a little bit of the conjugate base. Because if this base totally destroyed all of the weak acid, then we don't have a weak acid, we don't have a good buffer. Guess what? Ice. We're in 1 liter, so we'll call these as molarities. 0.50 molar, and then the NaOH is 0.20 molar. Don't worry about water, it's not part of the equilibrium expression. We do at the beginning have 0 and 0 this. Okay. Notice, okay, this is more it requires more thinking than a ICE table that you just rush through and solve for x. You got to realize what's happening here. Strong base, weak acid. The strong base will grab that proton, and all of that strong base will grab a proton. This is lower in number, so this is going to run out first. 0.20 minus. So every time this OH grabs a hydrogen, you're losing the same amount. Every time you grab a hydrogen off of that acid, you're gaining the same amount. Okay, and then you're also gaining, well, see, the sodium's actually a spectator ion, so I'm not going to worry about that, actually. Okay. Look at what's happening at equilibrium. Now we have 0.30 molar of the weak acid. We have no strong base, and now we have 0.20 molar of the conjugate base. When you mix these two, almost instantaneously, you now have a solution of the weak acid and its conjugate base. Okay, this is a good buffer. Okay, is there anything else I want to say? Now, if we have too much base, what if this was 0.6 moles? Then we're going to run out of the acid first. We'll put minus 0.5, and over here minus 0.5. We'll have 0 of the weak acid if we have equal amounts of base or more than what we start out with in terms of the acid. So these numbers now are important, okay? And you do want, fairly, it doesn't have to be identical, but you do want them pretty close, the concentrations of the acid and the conjugate base, the weak acid and conjugate base. The last thing I want to say about this is that this is, how should I say this, an approximation, because we're not considering the dissociation of this, right? We're not considering any Ka, but it doesn't matter because that's why we're using a weak base, a weak acid. The ionization is so tiny that it doesn't really matter. We may not have exactly 0.30 molar. We'll have less because of equilibrium. But you notice here, we haven't even talked about Ka, all right? So it doesn't really significantly change our results. We can say that we have these two concentrations. Okay, next is how they work. Letter C. How they work. Let us take that acetic acid buffer. Actually, let's take exactly the way we made it. We added these two, but we realized that when they react, you get these concentrations of the weak acid and the conjugate base. Is this thing focusing every time? Let me just fix that real quick. It is. Okay. All right. So those are the concentrations I'll be using. Let's have a 1 liter of 0.30 molar. Another way you could write acetic acid is C2H3O2, and it doesn't matter where you put the H. We'll put it at the end. And then the conjugate base concentration turned out to be 0.20 molar C2H3O2 minus conjugate base. Now, we're going to do this qualitatively. Probably in the next video, we'll apply numbers and do calculations, but qualitatively, what happens if add a little strong acid, HCl? What is the reaction? That strong acid, is it more likely to be neutralized by the weak acid or be neutralized by the conjugate base? HCl plus the conjugate base, C2H3O2, and honestly, I think it's more proper to show the counter ion as well. Like I said, even though this was made in the round bottom flask or in the beaker, if you had to get acetate from the stock room, it will be sold as a salt, or it will be existing as a salt. So let me put that Na, and we'll put it complex as an ionic bond. Keep in mind what's happening. You have an acid and you have a conjugate base. So let's do an acid-base reaction where the conjugate base grabs the proton, and we'll write it like this, C2H3O2H. And then what's left over? Oh, the sodium chloride. NaCl, you could write it as Na plus Cl minus. I'll just put here aqueous. We know that this is a salt and it will dissociate. What's important is that we took care of any hydronium that could have existed. If this was plain water, HCl plus water, we would get H3O plus, and the pH would shoot down. It would get more acidic. But what happened here was the conjugate base trapped the proton, and now it is in a weak acid. It's not being released, so the solution is not becoming super acidic. Alright, we have a weak acid now instead of a strong acid. This is all gone, right? We have enough conjugate base, because we only added a little of HCl, to neutralize all of we could think of it as the H plus ion. You want to try to write the reaction if a little base is added. Let's add NaOH. What would the equation in that case be? Okay, so I'll leave this as an example. Actually, let me give our buffer conditions here. This is our buffer. Okay. We add a little NaOH, and now we're going to use the weak acid, this species here, to neutralize it. C2H3O2H. Remember, this is acetic acid. And now the base is technically the OH minus, grabs a proton to create water. And what's left over? The sodium salt of the conjugate base, NaC2H3O2. So in this case, I drew the Na in the front. It doesn't matter, in the front or in the back. It doesn't matter. Wow, look what happened here. We took our weak acid. Oh, maybe this is a little bit unclear. I know it's weak, but when you pair it up with a strong base, the base is going to grab the proton, even though this is weak. The base is strong enough to say, I don't care if you're weak, I'm taking your proton with me. Alright, so it doesn't matter that it's weak, this reaction will happen, and we create the conjugate base. What you notice here is that on the product side, you have no hydroxide. Essentially, all of that hydroxide, all of that strong base, grabbed a proton and became water. Hence, the pH did not shoot up. The solution didn't get really basic. Now, buffers aren't perfect, okay? It will become a little more acidic if you add HCl, and it will become a little more basic when you add NaOH. The idea is it will it will not drop, the pH won't drop as much as it would if this was a pure water, right? If it was just water, if it's unbuffered, I mean you have all the acid. If it's unbuffered, you get this. See, no buffer, no conjugate base, and yeah, you get close to 100% H3O plus. That's acid, right? That's acid, and you have a Cl minus. Okay, and yes, this is, well, this makes it acidic, and the pH drops a lot. Okay, I think we are good with that. In the next video, we're going to do the same type of analyses, but now we're going to calculate. And what are we going to calculate? You guessed it. We're going to calculate the pH. And let's prove to ourselves that the buffer will resist a large pH change versus an unbuffered sample of water.